Hello, my name is Delaney Kirk, and this is Lab 2 of Physics 2212. So for the introduction, we're going to talk about the purpose of this lab, and that was to measure the distance dependence of a magnetic field due to a small bar magnet. And then we're going to compare those measurements from the experimental values to the computational model, and we'll look at the on-axis magnetic field and the off-axis magnetic field. So a couple previews of results. The right is what our computational model generated, and then we determined the strength of the magnet to be 3.145, and B net was 5.94 times 10 to the negative 6 Teslas. And then we have three main physics ideas we'll talk about. First is the Biot-Savart law, and that is that equation there of a point charge. And then second is dipole moments. We have the on-axis dipole, we have the off-axis dipole formula, and then we also have a linearized formula for that. And then finally we have the magnetic field equation that we use within our computational model. So for our models, the system is our Bower magnet and the surroundings is everything else. And like I said, we have two models. We have the experimental model, and then we have that computational model. Our initial conditions, our phone measured that the net magnetic field was 42 microteslas. However, in Atlanta, it should be about 48.6. So we had some discrepancy at the start. Then for the experimental model, we put two pieces of tape, and where they intersected was where the magnetometer was, and then we set our magnet at a distance away, and we recorded the X component of the magnetic field based on different R's. And then we did it where we would move the phone up instead of horizontally, and we determined, we recorded the net magnetic field based on different d-perps. This slide, we were able to determine that N was negative 3.01, while K was 6.29e negative 7. So then we set those two formulas equal to each other and solved for the strength of the magnet, and like I said earlier, it was 3.14. And then we went into our computational model. So here is the code. A couple things we changed. First, in line 23, we set mu magnet to 3.145, and then we wrote a function for the dipole, and so we used our formula from earlier and we plugged everything in correctly. Then we used this B scale and this distance just to kind of make our arrows look best, and we played around with those at the end. And then we had a couple different arrows for on-axis as well as perpendicular axis, and then we called our function here, and we repeated lines 67 through 70 for all the other arrows. We also did perpendicular arrows, so d-perp was set from our experimental model, and we kind of did that same process where we drew 4 total arrows. This was the results of our computational model. So as you can see, the orange arrows are the on-axis, that white thing is the magnet, and then the blue arrows are our perp axis, and that's why they're facing the opposite direction compared to the orange arrows. And then the magenta arrows are our off-axis, or our diagonal angle. So for our discussion, we're going to talk about similarities. Both of the models had the bar magnet as a magnetic dipole. However, the experimental model measured the net magnetic field, while the computational model measures the dipole. A couple sources of error. Like I said earlier, our initial B net was different than what it should have been in Atlanta, and then we had some difficulty finding the location of the magnetometer. So now if we oriented our setup so it didn't compensate for magnetic north, Earth's magnetic field would have interacted with the magnetic field we were measuring, and our measured readings would be inaccurate, and therefore the value of N and mu. If we had two magnetic dipole moments end to end, it would create a stronger dipole, and the B would be roughly double. Thank you.